Hi Chem 151 students, and welcome back for our next lecture on electrochemistry. So in the last lecture we introduced galvanic cells and cell diagrams, and also standard reduction potentials and how we may determine the cell potential using a table of standard reduction potentials. So now what we're going to do is go in a little bit more into the relationship between cell potentials and Gibbs free energy, and we're also going to talk about applications with batteries. The last lecture was a little bit too long. Maybe this one's going to be a lot shorter. Maybe I should have cut them a little bit differently, but you can feel free to watch that one in two separate parts if you like. I felt like all of that material went well together though, but it ended up being about an hour-long video. But anyway, we talked about here standard cell potentials. Now we're going to talk about cell potentials under non-standard conditions. So just like we had delta G standard, where we have 1 atmosphere pressure of gases, 1 molar concentration of aqueous things, and standard cell potentials where we had the same thing, 1 atmosphere pressure for gases like hydrogen, 1 atmosphere or 1 molar concentration of aqueous things like H+ ions. What if we are at non-standard conditions, which is, the more common state? We're not usually at standard state. We want to have an equation where we can take the standard cell potential and make an adjustment to get the non-standard cell potential with the realistic potential that we would have in our realistic galvanic cell or battery. To do that, we're going to use an equation called the Nernst equation, and this Nernst equation is actually not going to be an equation that's new. It's going to be derived from an equation, this equation here that we learned in the last chapter. So delta G equals delta G standard plus RT ln Q. Now, we already saw that delta G is defined as minus NFE, and delta G standard is minus NFE standard. So what we can do is we can plug into this equation we learned in the thermodynamics chapter. We can plug in for delta G minus NFE. And we can plug in for delta G standard minus NFE standard. And so that gives us the equation minus NFE equals minus NFE standard plus RT ln Q. Now obviously this equation is a bit ugly, so what we'd like to do is divide both sides by negative NF. So what this means is we're going to divide this by negative NF, so that will cancel these. We're going to divide this by negative NF. Remember, we're going to divide both terms by negative NF. So we're also going to divide this by negative NF. And so here we get E on this term, we get E standard on this term. On this one we get, since there's a negative here, we're going to get negative RT over NF ln Q. And this is referred to as the Nernst equation. The truth is that I always have a hard time memorizing these. Now, the way that and you don't have to memorize these, but I think it's useful to memorize these. I always used to have a hard time remembering if it's a positive or a negative here. And so the way I remember that is based on the way the equations work. So if, for example, here, when I think about this, I think, well, if Q is very small, what that means is I have a lot of reactants and not a lot of products. So that reaction is likely to go forward. And so this must be a positive, because if I have a small q, that makes this natural log negative. And so that makes this whole term negative, and that favors spontaneity. That makes sense. If you have a lot of reactants and not a lot of products, as we discussed in the last lecture, that means the reaction is probably going to go forward. And so that helps me to remember that this is a positive. And then I don't really remember that this is a negative. What I do is I have this equation memorized, and not pure memorized, basically interpreted in my mind in the way I just described. And then I can easily divide, I can easily plug these in as we just did and get this equation, and that helps me to remember that this is a negative. You'll notice I try to teach you all the little tricks that I have for not memorizing things. I always memorize as little as possible because memorizing is weak. It's fragile. You don't want fragile knowledge. You want strong knowledge, right? Likewise, we can do a similar thing here, though, too. A spontaneous cell will have a positive E, right? And so if this Q, again, is very small, meaning there's a lot of reactants, that means the reaction should want to go forward, right? So if Q is small, that makes this whole thing negative, which makes this whole term over here positive, and positive favors a more spontaneous cell. So that makes sense. Imagine if you had almost all reactants, this would be very negative, which would cause this entire term to be very positive, which would make this E positive. And of course, the cell would want to go forward. It would be spontaneous. The reaction would be spontaneous. Now, your book likes to do this thing where, since this equation has a lot of constants in it, R is constant, F is constant, and T is usually 298 Kelvin. So what your book does is it actually uses a modified version of this equation in which, first of all, for some reason, and all the books do this, they take the natural log Q and instead turn it to a base 10 log. So the natural log of X is equivalent to 2.303 times the log of X. So we say here that E equals E standard minus 2.303 times the base 10 log of Q. So what we've done is taken the natural log and now converted it to a base 10 log by multiplying by 2.303. Why? I don't know, but your book uses this equation over and over, so I think it's important that you're aware of it. Finally, R is 8.314 joules per mole Kelvin. F is 96,500 coulombs per mole of electrons. And so if you plug those in and you plug in 298 Kelvin for temperature, we can calculate those. So it'll be 2.303 times 8.314 times 298 divide by 96,500, and we get 0.059, about 0.0592, and the units here will be volts because they're going to be joules times coulomb, or joules, sorry, divide by coulomb. So the unit ends up being volts, and we get then base 10 log Q. So this equation is very, very frequently used by your book. It's handy because you don't have to do as much junk. Like, it's very easy to use, and so I highly encourage you to use it, but it's not as easy to interpret. So if you're trying to understand the equation, I think you should start here or here. But if you're just trying to punch in numbers and get an answer, this is a really good equation to use. And so I will use this for the punching type problems. But when I'm talking about like interpreting the equation, I'll use this one instead. So this is the kind of question we would use to use the Nernst equation to solve. So consider a galvanic cell that uses the following reaction. We got copper being oxidized to copper 2+ ions here, and we got iron 3+ ions being reduced to iron 2+. What is the potential of a cell at 25 degrees Celsius that has the following concentrations? So we're going to use the equation E equals E standard minus 0.0592 volts over N log Q. So what we need to solve for this is we need Q, we need E standard, which we're going to have to use the standard reduction potential table for, and we need N, the number of electrons transferred in this reaction. So first of all, let's calculate E standard. To calculate E standard, we're going to have to break this down into its oxidation and reduction equations. So the oxidation here is the copper being oxidized to copper 2+. So to do that, and to balance this, we add 2 electrons. And so now it's balanced, copper's balanced, and the 2 electrons here balance the charge. And then next, we've got iron 3 plus. It gains 1 electron to create iron 2 plus. Now notice that the electrons being lost are not equal to the electrons being gained. So we're going to have to multiply this reaction by 2, but that's not going to affect our potentials. So let's go and look up the potentials though from our appendix. So in the appendix, for the reduction of copper, we have 0.34, but in this question we have the oxidation of copper. So we're going to write the oxidation potential, which will be this potential with the sign reversed because the equation's reversed. So it's going to be negative 0.34 volts. Then we have to look up the reduction potential for iron 3 plus being reduced to iron 2 plus. And that is right here. And its reduction potential is 0.77. So we'll write that there. And again, if we're going to add these, just as a note, we're going to add these to create the overall reaction. Notice that there's 2's in front of the iron. This is because we need to multiply everything by 2 here in order for the electrons to cancel out, and they must cancel out. So overall, we get the reaction copper plus 2 iron 3 pluses plus copper 2 plus makes 2 iron 2 plus. And then to get the overall reaction, we add the oxidation potential to the reduction potential, and we get 0.43 volts. Now, I do want to say something on a side note, is that if you guys are watching other videos or even reading some parts of your book, they may give you an alternative equation. So the equation I'm giving you here is that E standard or E oxidation plus E standard reduction equals the E standard for the cell. And that's the equation I like to use because it's, I don't know, it just makes more sense to me, but it doesn't involve any abstractions. But another alternative form, so alternative form is, and I don't want to confuse you, but I want you to make you aware of this because you may see this elsewhere and be confused. See, we'll say E standard cell equals E standard cathode minus E standard anode. A lot of books and YouTube videos will give you this equation, and the reason why it's like this is because E standard anode here what they're referring to in E standard anode is this is a reduction potential for the anode. Is they're saying the negative of the E standard. So they're saying minus the negative of the E standard reduction potential. Okay, so what I'm getting at is that I'm having you add them and see this negative right here. That's this negative right here. So something that some of my students have done is they'll go somewhere else and find this equation, but what they'll do is when they put the E standard anode, they'll change the sign. But what they've done is they've changed the sign twice. This changes the sign too. So here, notice I'm adding because my oxidation potential already has the sign changed. But in this equation, this is there to change the sign of the reduction potential to make it an oxidation potential. So I'm going to say, if you're using this equation, I'd say be careful with this. I don't use it, okay? I'm just going to tell you it's out there. But be careful because this negative is meant to change the sign so the reduction potential becomes an oxidation potential. But I do that separately because I say this is an oxidation potential, not a reduction potential. I need to change the sign, and then I just add them to get the overall cell potential. This builds in the changing of the sign right here. So when they say E standard anode, they're saying the reduction potential of the E standard anode, and this negative is meant to change the sign. but I already changed the sign. So don't change the sign twice, is what I'm saying. I recommend doing it my way. But if you like E cathode minus E anode, the purpose of this is just to plug in the values straight from the chart. So yeah. So if we did it this, if we use this one, it would be in our equation here, our E standard cathode would be 0.77 volts, and then we'd be minus 0.34 volts. And that's directly from, that's just taking the numbers directly from the chart. 0.77 for the anode, or for the cathode, and 0.34 for the cathode. This negative changes the sign, but notice I already changed the sign to make it an oxidation potential. So when I add them, I get 0.43 volts. So be careful if you're going to use E cathode minus E anode. These are indicating both reduction potentials. What I do is I change the reduction potential to an oxidation potential by changing the sign. That's what this negative is doing here. So I just wanted to point that out because I've had my students go learn things somewhere else and then and say, oh, I like E cathode minus E anode. Maybe you do like it and you can use it, but just note that this negative is changing the sign to make the reduction potential an oxidation potential. You can just change the sign yourself and make it an oxidation potential. Okay. So we've got the E standard cell now anyway. And the N here, you can see the N is going to be 2. 2 electrons lost, 2 electrons gained. So we've got the N as well. All we need now is the Q. So from the previous slide, we determined E standard cell is 0.343 volts. And our N is 2. I'll just write that over here. We already figured out our N equals 2. So all we need is the Q now. So let's calculate Q. So we've got, so E equals E standard minus 0.0592 over N times the log of, okay, now we're going to put in Q. So the reaction was, and actually I want to write it here so that you can see it. So Q here is going to be products over reactants. So it's going to be the copper concentration times the iron 2+ concentration squared over the iron 3+ concentration, the reactant, squared. And we're not including the copper because it's a solid, it's not aqueous. So this is going to be our Q. And so this is the Q right here. Copper concentration times iron concentration squared over iron 3 concentration squared. Now we just have to plug all these values in. So the E standard is 0.43 volts. The N is 2. And then base 10 log copper 2+ concentration is 0.25 molar. Iron 2+ concentration was given in the problem as 0.2 molar. We're going to square that. Then divide by the iron 3+ concentration, 1 times 10 to the minus 4 molar, and we're going to square that. And so now let's punch that in the calculator. And be very careful. If you're going to do it all in one shot like I am, be very careful. So I'll show you here. 0.43 minus 0.0592 divide by 2 times the base 10 log of 0.25 times 0.2 squared divide by 1 times 10 to the minus 4 squared, close parentheses. And we get to 2 after the decimal, 0.25, and our units are volts. 0.25 volts. And so again, the standard cell potential is for 1 molar concentrations of everything, or 1 atmosphere pressure of gases. Realistically, that's not probably going to be the case. The concentrations will be different. So at these different concentrations, the E for the cell was 0.25 volts. And so that's how we use the Nernst equation to determine the actual E standard of a cell under the normal the actual E of a cell, the voltage of a cell at the non-standard conditions. As a side note, we've been using pH electrodes in the lab, and the pH electrodes operate off of electrochemical principles. So you may have noticed when you were calibrating your pH electrode, it read a voltage because there is an electrochemical cell inside your pH meter. And what you did in the calibration is you related a particular voltage to a particular pH. And so this is the design of a pH electrode like this. So it has a silver wire coated with silver chloride. There's a reference solution of dilute hydrochloric acid, and then there's a thin glass membrane separating the solution from the solution of the unknown pH. What happens is that the membrane is thin enough that H plus ions can pass through it, and so the concentration of the H plus inside changes, and due to that fact, the voltage of the electrochemical cell inside of here changes due to the different concentration of H plus, and based on that change in voltage, you can determine the concentration of H plus in the solution that you're dipping it into. Pretty cool, huh? Finally here, standard cell potentials and equilibrium constants. So just like we could relate delta G's to delta G standard to equilibrium constant, we can relate E standard to the equilibrium constant. So delta G equals minus NFE standard, or delta G standard rather, equals minus NFE standard. It also equals minus RT ln K. So what we can do is we can put minus NFE standard equivalent to minus RT ln K. And so we have minus NFE standard equals minus RT ln K. And again, if we want to solve for E standard, we divide both sides by negative NF. So we're going to divide here by negative NF, and those will cancel. Divide here by negative NF, and our negatives will cancel, and we'll get E standard equals RT over NF ln K. And again, remember I told you I always used to have a hard time remembering what the signs were. That's why I decided I wouldn't try to remember. I always just derive it really quick since I know these equations. I do have this one memorized. There's kind of no choice there. This one I derive from delta G equals delta G standard plus RT ln Q. But if you have those, you can just simply derive this in your head real quick if you're used to it. Now again, like the other equation, your book likes to convert this base 10 log, this natural log to a base 10 log. A lot of books do this for some reason. So just generally mathematically, a natural log of x or any number is the same as 2.303 times the log of that number. And so we can replace natural log of k with 2.303 times the base 10 log of k. We still have the RT and the NF. And then we can plug in 8.314 for R. We can plug in 298 again for Kelvin for temperature, and the Faraday constant 96,500 coulombs per mole of electrons, and we get that same number, 0.0592 volts over N times the base 10 log of K. And again, if you're doing calculations, this is a much easier equation to use with less constants, random constants here. So I can understand why they do it. I always think it's weird though that they always like to turn the natural log to a base 10 log, but this is the equation that you'll commonly see your book used and when calculating K or E standard based on this equation. And what is how does this relationship go? Again, an important part of being able to do these problems is to interpret what the equations mean, not just to plug in numbers to it, but to understand the way the numbers work in the equation. And so if k here, so if k is 1, what that means is that you have the natural log of 1 here, but the natural log of 1 is 0, so that makes this whole thing 0. So when k is 1, that indicates a E standard of 0 for the E standard. If k is greater than 1, well, I'll start with k is less than 1, then you get a negative number here, so E standard would be negative, so we can see these negative E standard values here. If k is greater than 1, then this number, this natural log of a number greater than 1 will be positive, so your E standard will be positive there. And that's the relationship dictated by this equation. So now that we've got the normal thermodynamics, we've got electrochemistry, and we've got equilibrium covered, we have 3 different ways that we can determine equilibrium constants. And these are all used by various experiments to determine and to confirm in different ways the equilibrium constants of various reactions. One is we can determine an equilibrium constant from concentration data. If we measure the concentrations at equilibrium, we plug them into the equilibrium constant expression, we get an equilibrium constant. If we have delta G standard, we can use that to figure out K. So using the equation is usually written delta G standard equals minus RT ln K. If we solve that for the natural log of K, we get natural log of K is negative delta G standard over RT. So if we have delta G standard, that's a way that we can get the equilibrium constant for a reaction. Finally, if we have electrochemical data on a reaction, we can use that to determine the equilibrium constant of a reaction. So this is from the equation we just had, which was E standard equals RT over NF ln K. And so if we solve this for natural log of K by multiplying both sides by NF and dividing by RT, we get that the natural log of K equals NF E standard over RT. So there's 3 different ways now that we can use to determine an equilibrium constant, which makes for some very interesting questions on standardized exams and such. And also just various practical ways of figuring out the equilibrium constant. So those are the 3 ways we have now. Last, I want to finish up this lecture with some general information about batteries. Now, if you're not interested in batteries, I'll say you don't have to watch this. I'm not going to be testing you on battery chemistry because the chemistry of realistic batteries is kind of complicated. And it often involves a lot of real practical considerations. So as we saw before, when a battery is operating, often the anode or the cathode can be degraded. Like when we talked about the zinc, as the electrochemical cell went forward, the zinc electrode would dissolve and make zinc 2+ ions, and the copper electrode was copper was being deposited onto the electrode, and the electrode was getting bigger. And so these realistic situations that occur in electrochemical cells mean that some electrochemical cells, once they've gone in one direction, they cannot be reversed very easily, whereas other battery chemistries can be reversed. And so that leads to a situation where we have some batteries that are rechargeable, meaning we can reverse the reaction that gave us the energy and get the original battery material back, and some are not. It all depends on what kinds of chemical reactions are happening in the battery. One of the most robust rechargeable batteries that is commonly used is the lead storage battery. This is the battery that's you probably have in your car. So that is constantly discharged to start your car and then recharged as your car is driving. And for that battery, the anode is composed of solid lead, and it's in a sulfuric acid solution that includes bisulfate ions. And when the anode is when it's operating here and the anode is losing electrons, it makes solid lead 2 sulfate and H plus ions and 2 electrons. And then on the cathode side, there's lead oxide solid, and this is reacting with acid that's in the battery. The battery acid is sulfuric acid, so there's H plus ions and bisulfate ions from the sulfuric acid. And then 2 electrons are gained, and this produces lead 2 sulfate and water. And so the overall reaction is solid lead and lead 2 oxide reacts with acid and bisulfate ions to produce solid lead 2 sulfate and water. And this reaction is what provides the energy for your car. Some people use it to store solar energy as well. They use car batteries. This is what a lead storage battery looks like, physically speaking. So it's in a sulfuric acid electrolyte, and there's alternating grids of lead and lead 2 oxide that are consumed in the battery process. And then those grids, that the lead and the lead 2 oxide can be redeposited onto these grids when the battery is charged up. And so this makes this battery very robust, very rechargeable, and so they operate very well for a long time, and they're reversible. And so that's why this battery continues to stick around. Its downsides is it's heavy, it's filled with concentrated sulfuric acid, which isn't good if it gets opened up. It's heavy because it's got lead in it too, but it's very effective. And even despite its weight and its downsides, it's reliable operation, and its easy reversibility makes it ideal for an application, for heavy applications like a car. You wouldn't want a lead acid battery for your phone probably, or your laptop or something like that. So this design is very good though for cars, and it continues to be used for that reason, despite some of its downsides. Now regarding small batteries, like the kinds that go in your devices, like AAAs and AA's, there's several different forms of battery chemistry involved in those. For the non-rechargeable batteries, most of them involve a zinc anode, and then the cathode is what varies. So in this so-called dry cell battery, these are also what are often called heavy duty. If you go to the 99-cent store and you see some batteries called heavy duty batteries, that's what this is. It means like it's basically a very low performance battery with it can't store a lot of charge, but it's cheap, and people don't often use them unless they're really cheaping out. But the cathode is a manganese 4 oxide in an ammonia, aqueous ammonia, which is really in the form of a paste. So the 2 electrons are gained here, and it produces manganese 3 oxide and ammonia and water. And so here's what that looks like on the inside. You can see a picture here. It has a graphite rod, which serves as the physical cathode for the carrying of the charge. But it's the MnO2 that's actually gaining the electrons and being reduced. It's in this paste, which includes the ammonium chloride and zinc chloride in order to carry the charge. And the anode is actually the outside of the battery. It's the zinc. And this is actually why you can't recharge these batteries. They tell you not to recharge them because they may open up and leak. It's because if you're recharging the batteries, you can cause the zinc to dissolve, and the zinc is the anode, it's the casing as well, and so that can lead to ruptures in the casing and for the contents to leak out. So you can see here is a Radio Shack heavy duty battery, the kind of battery you probably wouldn't really want, but often comes with remote controls and stuff that want to give you a cheap battery. Now, the most common batteries that we use for AA's and AAA's are the alkaline batteries. These are called alkaline because they do have a zinc anode, but this is in an alkaline environment with hydroxide ions. And the oxidation involves the formation of zinc oxide and water. The cathode is exactly the same as the heavy-duty battery. It's the manganese 4 oxide cathode, manganese 4 being reduced to manganese 3 here and producing hydroxide. So these are called alkaline batteries because their big difference between those and the heavy-duty batteries is the presence of hydroxide ions or base in the battery. And when it comes to rechargeable batteries, back in the 90s, the common rechargeable battery was the NiCad or nickel cadmium battery. Now these batteries, they could be recharged unlike the alkaline or the heavy duty batteries, but their big problem was that they couldn't be charged very many times. They quickly degraded in performance, and it was because, as I was discussing before, if the anode and the cathode materials are not made in the reverse reaction to be exactly like they were when you first got the battery, their performance will slowly degrade over time because their physical form will not be maintained through many discharge and charging cycles, and they won't be the same as when the battery was first produced. So that's especially true for non-rechargeable batteries. For nickel cadmium, they could be recharged like 50, 100 times before they could hardly hold the charge anymore. They're called nickel cadmium batteries because the anode is cadmium, which is oxidized to cadmium 2 in a basic environment. And then the cathode is a complicated nickel oxide hydroxide complex. It's a transition metal complex, and this forms nickel hydroxide. And so this is also you could say alkaline. It has basic components in it, but the cathode has a different makeup as well as the anode, which results in higher performance for rechargeability. Later, there were better batteries that came out called nickel metal hydride. And many of the rechargeable batteries are still nickel metal hydride to this day, although there are lithium. I mean, in your phone, you have lithium rechargeable batteries, probably, or your laptop. They're called nickel metal hydride because the anode is a metal hydride. The metal varies, so the M here stands for metals, and then it has hydrogen atom attached. The metal is oxidized and the hydrogen removed here, and so the metal the metal is oxidized, and so that its H comes off as an H plus and makes water with the hydroxide, and the metal then, which actually was negatively charged here, becomes oxidized and an electron is lost. And then the cathode is the same as the nickel cadmium battery with this nickel oxygen hydroxide complex here. So a very similar chemistry. The big difference was the cadmium was replaced with this metal hydride, which resulted in more robust and stable performance when you had a recharge. Now, lithium-ion batteries have a lot of different chemistries. In general, what came before the lithium-ion battery was a lithium battery. The anode was solid lithium, which was oxidized to lithium positive 1. And the advantages of lithium batteries is that lithium is the lightest known metal. And so it results in very light batteries with higher charge density per weight. And that's why the chance to have lighter, higher performance batteries later on would rely on coming up with some very strange anodes that are not just metal. Lithium being the lightest metal here. You're not going to have a metal anode that is any lighter than lithium, giving you the same amount of charge. The cathode, as you can see, is the same or similar to what it was in the alkaline batteries. And the manganese 4 oxide. Lithium here is also present in the cathode, and you make a lithium manganese oxide type of complex here. And so, as I said, the battery, these are just very general equations because the battery chemistry actually is very variable and complicated. An improvement on the lithium battery was a lithium ion battery. And the lithium ion battery involves a lithium carbon type of material. So a material involving lithium atoms that are embedded in a carbon matrix. And the advantage of this is that carbon is light, and also the lithium ions which are embedded in the carbon complex, they are more likely to maintain the anode structure through many charge and discharge cycles, because the lithium atoms are locked in place essentially. And then the cathode involves a complex of lithium, cobalt, oxygen. And so you can see that the chemistry becomes very, very complicated. And this is just general lithium ion battery chemistry. There's actually lots of different variable versions of this. So it becomes more and more complex. I'd say this is actually really leading to the extent of my knowledge on batteries. But if you're interested in batteries, I encourage you to Google more and find out more. And then finally, actually, what I think next time when I lead off, I'll talk about the fuel cells. So these are kind of like batteries, but they operate a little differently. At this point, I think I've gone on long enough for this week. And next week or later on, we will finish electrochemistry and then move on to the end of the course. So I will see you next time. All right, have a good one.